Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
So we set these blocks of basically alcohol ice in a big beaker or a container on a heater, right? And we're like, it's going to take a while for this to heat up. And so we head out to lunch and come on back, and there's a fire truck and all these people standing outside the building. And it turns out that, stuff's pretty volatile when it's liquid, and the smell was bothering some people in the neighboring lab. And so they pulled the fire alarm on it and cleared out the whole building. And so the hazmat team was in there, getting everything cleaned up and turned the heater off. And so it'd go back to solid. And so I basically cleared out a whole building at NASA or at JPL for a whole day and still didn't get yelled at. It's more like, yeah, you guys probably should have thought a little bit about the volatility of that sample. And I'm like, sorry.
That's a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, how scientists are solving research issues, and what tools are helping them better understand measurements across the entire soil-plant atmosphere continuum. Stay current on applied environmental research, measuring methods, and more. Thanks for spending time with us. All right, let's get started. On May 25, 2008, NASA's Phoenix lander successfully landed on the surface of Mars and used a robotic scoop arm to deliver Martian regolith samples to the suite of instruments on the deck of the lander, with one exception. The Thermal and Electrical Conductivity Probe, TSIP, designed by a team of METER research scientists, was mounted on the knuckle of the robotic arm and made direct contact with the regolith. It measured thermal conductivity, thermal diffusivity, electrical conductivity, and dielectric permittivity of the regolith, as well as vapor pressure of the air. Today, we'll interview two of the scientists who were involved in the development of the TSIP, Drs. Doug Cobos and Colin Campbell. Hey guys, thanks for joining us today.
Hey, Brad.
Hey, Brad.
All right, so let's jump right in here with my first question. It's a cool story, Mars and all, but why should anybody on Earth care about the thermal properties of Martian regolith?
That was really one of the things that we were a little confused about initially. We were excited that we could work on a NASA project, and that sounded really cool, but understanding why we really needed to know thermal properties on Mars was a bit confusing to us. But in general, as I understand it, the thermal properties of the regolith helps us understand what the climate models need to have inside them to generate an understanding of the climate of Mars. And even though we were only measuring something, within just, 1 meter total area, we don't know anything about it right now, or didn't at that time. And so being able to understand what the thermal properties of the regolith would help us be able to extrapolate to the surface and therefore gather climate models. Doug, you know more about that, though.
The Mars Global Surveyor had done remote sensing of the thermal properties of the regolith. They were measuring thermal inertia or thermal admittance, as we like to call it in soil science. And so they had mapped the entire surface of Mars remotely, but they needed a ground truth for that. And that's really where TSIP came in, is that we made those measurements directly at one site and were able to ground truth the remotely sensed measurements. And those measurements actually lined up really well. So I think it gave the Martian science community a lot more confidence in those measurements by that thermal emission spectrometer aboard Mars Global Surveyor. One of the other important things about the thermal measurements from TSIP were that the suite of measurements that we made, specifically the thermal diffusivity, allowed us to calculate the diurnal damping depth, which is kind of the depth in that regolith that the energy from the sun penetrates on a daily basis. And one of the interesting things, and it's not a surprise, is that the diurnal damping depth that we measured of about 6 centimeters lined up really, really well with the depth to the ice layer. So, when the robot arm scooped away the regolith on top of that ice layer, it was just about that 5 or 6 centimeter depth. And so another bit of importance there, I suppose.
So how did NASA even find out about METER? How did that come about? How did they approach you?
On a Friday afternoon, I got a call from Martin Buehler at the Jet Propulsion Lab. And at that time, I really wasn't kind of tuned into what jet propulsion, the JPL, was. And he said, "Hey, how would you like to participate in this grant? We're putting together a proposal to fly on the Phoenix lander to Mars." And apparently, one of his colleagues had seen our thermal properties analyzer, which we called the KD2 at that time, at the American Geophysical Union meetings in San Francisco. We were pretty small at that time as a company, but we did attend that meeting, which involved a lot of different scientists. So we were particularly interested in the biologists and the hydrologists who attended that meeting, but also planetary scientists would go there. And our friend from JPL was just going through the exhibits and found the KD2 on the table there and said, "Hey, this looks interesting. Could you guys stick this into Martian regolith?" And one of our colleagues, Matt Galloway, was there and said, "Well, I'm not sure, but maybe. Just here's our card. Call us up." And so that led Martin to call us on a Friday afternoon and say, "Hey, we're putting together this proposal and we'd like you to be a part of it with your KD2 sensor. What are your thoughts?" And when I've thought about working with someone like the Jet Propulsion Laboratory or NASA or something like that, I always imagined companies that had, a bare minimum of 1,000 employees participating. And so I told him, frankly, I don't see any way we could do this. We're just a 25-person company at that time. I think that was about 2002. And we just simply don't have enough resources to go on this mission. But for some reason, and I'm not really sure why, Martin was undeterred by that. He talked to his friend Mike Hecht, and they actually took a plane from Southern California to Pullman on Sunday, and were there to meet us on Monday morning in Pullman, Washington, way away from pretty much anywhere in the world, and sat down and talked to us about the mission they were putting together. And that's basically how we got started. It's practically impossible, in my experience, to say no to one of these opportunities once somebody's there talking about making measurements on another planet. By the end, we were hooked. We wanted to go.
So in this partnership then with NASA, are you guys flying back and forth, whether down to JPL or other NASA locations? How did that work out?
Well, let me start the story, and then Doug can kind of fill the details. We wrote a proposal with them. It was extremely fast. I remember this being on the order of just a few days. But one thing we did was to put in the addition of another person, and that's where we got to hire Doug. And that really was the start of being able to be successful as this project.
Could I just add that you guys are totally crazy hiring somebody green like that to come in and work on a project like this? I mean, like I said, the chances of success here were about 0%, but somehow this worked out. I credit the JPL guys.
Yeah, thanks, Doug.
Yeah, so the way that worked was most of the engineering work was done here at Decagon at the time, and then we would have those guys up, or we would travel down. It was almost all at JPL. I don't think we ever actually went to NASA Ames or any of the other NASA outposts there, but we'd spend some time down at JPL, especially for the design reviews, and those were some of the things that were the most nerve-wracking that I can remember, was especially this one step that they had called the critical design review, where you got to go and show your design and show your results in front of a panel of highly experienced and brilliant NASA scientists and engineers, and they got to pick apart your design and tell you if it was going to be a go or a no-go, and if it was going to fly or not. And I recall losing a lot of sleep over that, but then it turned out to be pretty chill. I mean, we had done a lot of the work up front, and it ended up working out okay. But yeah, there wasn't too much back and forth, I guess. A lot of it was communication via emails and plans and test results and things like that.
But Doug, when you look back on this, that now, and I mean, we've now had nearly 20 years of instrument development under our belt. I mean, we were super green there. You were brand new. I was 2 years into this. Does it shock you a little bit that, we were as confident as we were going into there trying to make something to go to Mars?
Yeah, it does. And I mean, in hindsight, it absolutely does. And we've evolved a lot as a company and as a instrument development group since then. I mean, a whole lot. But one of the nice things about that project being, my first one was that understanding how technical risk is evaluated at a highly professional level and at a level where if something messes up, then a whole mission fails. That was really useful and I think formative. I mean, I think that the folks around here will attest to the fact that I tend to be more of the critical thinker on our projects and try and identify risk and try and mitigate that before we release things. And I think a lot of that was because of this project.
I'm glad you brought that up because we learned a ton from JPL about instrumentation development and about trying to analyze what were the most critical risk-bound pieces of the project, and also how to really get something that will fly without trying to perfect it too far. I'd love to hear a little bit more what you think on that, Doug.
Well, those guys that we worked with were just a really great team because they had an unwavering can-do attitude, and most things that make it off the surface of the Earth and go into outer space have a whole boatload of requirements with radiation hardening and various things like that. And we got waivers for nearly all of that because we entered this project way late in the game and there was no way that we were going to be able to qualify parts in time. And their idea was, well, any of these components would fail at a way less than 1% rate, over the duration of this mission. And so let's just write the waivers and hope for the best and play the odds. And it turned out to work okay. So really appreciated their willingness to do that because that simplified our lives quite a bit.
I think a lot of the stuff that we did was off the critical path. I mean, I think, at least in their mind, if TCP completely breaks, that's not going to ruin the mission. So it's sitting out there on the knuckle, as long as it doesn't freeze into the soil overnight. That was a concern. Mm-hmm. Then we're going to be fine. But that allowed us a lot of freedom on this measurement to be able to actually make, a whole suite of measurements that typically wouldn't be found. A lot of these things are really tight. We were measuring even things like wind speed, relative humidity, water content, electrical conductivity, thermal properties, a long list of things. Because we had some of these waivers, we could do a lot of things a little more freeform than might be traditionally seen.
Yeah, that's absolutely true. And their can-do attitude kind of bled over into our can-do attitude, especially your dad's, Galen Campbell's attitude about making various measurements, because we didn't even think about measuring vapor pressure or relative humidity until way, way late in the game. I mean, we were almost done with all of our design reviews when they said, hey, what do you guys know about measuring vapor pressure and relative humidity? And turns out the whole other half of our company is, that's what we do for a living. And so we threw that measurement on late in the game. And some of the most interesting results came from the humidity measurement.
But Doug, to what do we attribute the fact that we were the only sensor, according to Mike Heck, that worked for the entire time on this mission?
Colin, I quite frankly attribute a lot of that to Mike and Martin and your dad, that your dad's engineering work on this, especially in terms of electronics, was very good within the scope of the mission. And I'd put Greg Cardell in there as well, that a lot of the folks from JPL that were collaborating with us, they knew what they were doing. And so I think that helped us be successful.
So Doug, as lead engineer, can you tell us a little bit more about the development of the sensor?
Yeah, so got to give almost all of the engineering credit to Galen. One of the interesting parts about this project was that TSIP took the place of another instrument, and we had to use the same interface, same analog interface as that other instrument. And so it had to be designed around a certain set of criteria that were pretty difficult to design around, but Galen made it happen. And then it was just iteration from that point. I mean, it was make the measurements, it was test, it was find problems, it was, go back to the drawing board, revise, test some more, revise, test some more. And so it was pretty much an endless loop of testing of all the measurement functions and the communication functions. And until we finally had success with it. And yeah, there were all kinds of setbacks along the way, but nothing that we ended up not being able to overcome.
I remember just the schematic drawing, a big sheet of paper with schematics, multiple sheets, I think, and you poring over them, trying to figure out how to do this and that, get all the communication done. Those were difficult times.
Yeah, and some of the testing was pretty intense. I remember one of my early career memories was when we got our first set of PCBs for this, and we put all the components on those PCBs. And back in those days, we used to do that by hand, okay, instead of with the pick and place, the surface mount machine. And I got those on a Friday, and none of them worked. And so I spent the entire weekend in there troubleshooting those things, looking at schematics, measuring voltage levels, digital logic levels, all this stuff, and finally got a couple of them to work. There were components backwards, components not stuffed at all, wrong components. I mean, it was a big old mess, and I was so fried by that experience trying to get those things to work, and it totally shook my confidence. In fact, I think the next week, I told the NASA guys, I'm like, we're going to have to restuff all these boards. Like, we're going to have to use your pick and place and do this because, oh man, I had zero confidence after that. So that was just one example.
So you got it done, got it produced, got it shipped off, and then do you just kind of sit back and let JPL take care of the rest?
Yeah, so we got it all done, got the design done, got all the parts made, and shipped them down to JPL, and they put everything together and put together a series of TSIP instruments. So they had the actual flight unit, the one, and then a flight spare, and then several other backup units that went to various, generally academic institutions to get characterized and help with the calibrations. And so once everything was assembled, went down to JPL and spent a lot of time with Greg Cardell, which was kind of my counterpart over there. And by spend a lot of time, I mean spent 2 weeks down there, and those were probably close to 100-hour weeks. That it was get up early and work on calibrating the flight unit all day, go to bed late, sleep for 5 hours, and back up and do it again 7 days, 2 weeks straight. It was pretty intense, and we.
Didn't you bring your wife on one of those trips?
Yeah, that was when my oldest was just a baby, and she was at Santa Monica on the beach, and I'm like working, these crazy hours and bleary-eyed. I didn't even see her. I pretty much didn't even see her. I was in bed after she was, and out of bed before she got out of bed every day. Yeah, but that was super intense and very rewarding until NASA was putting this all together. And so they had that calibrated flight unit, and they bolted it onto the robot arm. And then they plugged it in. And as it turns out, even though there was somebody plugging it in and somebody looking over their shoulder, signing and certifying that they plugged it in right, they plugged it in wrong and powered it up and compromised it, or potentially compromised it. So then had to go back down and spend another 2 weeks qualifying and calibrating the flight spare, and so had to do this process twice. And so it was a little bit disheartening, but again, we got it done, and it ended up flying.
And this is all on a timeline, right? So when you put this all together, Doug gets that instrument done, and they go put it in Colorado. Doug, I can't remember it.
At Lockheed, right? It was at Lockheed Martin, I think, that they.
Yeah. So they put it all together, and then they zip it all in the pouch, right? And then they truck it over to Florida. So, all of these things, everything's got to come together in this fantastic way to be prepared for the launch. And, I remember when they called up and let us know about the flight unit being fried, it was like, oh my gosh, how can this happen? This is NASA we're talking about. They don't break stuff.
But what's interesting, and I got to give a shout out to the culture at NASA and JPL. One of their mantras was that they don't sit around and assign blame and blame people for issues. What they do is they try and learn from it, and then they move on and continue on trying to have success. And so, whoever plugged it in wrong and signed off on it, they probably didn't fire them. And I had my own foibles that I didn't get yelled at about. I guess I'll go ahead and tell the story. One of the most embarrassing things that I've done Okay, this is like second tier embarrassing, but it was during one of those 2 week calibration events. It must have been during the first one. We were calibrating the dielectric permittivity function of the TSIP, and we were using different alcohols that had different known dielectric permittivity to construct that calibration. And so we had just looked up the book values of dielectric permittivity for all these alcohols and got in the right set. And we opened one up and we're like, oh crap, this stuff's a solid at room temperature. And so we look it up and we're like, oh, okay, we just need to get this up to about, 30 degrees C and it'll liquefy and we can use it. And so we set these blocks of basically alcohol ice in a big beaker or a container on a heater, right? And we're like, it's going to take a while for this to heat up. And so we head out to lunch and come on back and there's a fire truck and all these people standing outside the building. And it turns out that, stuff's pretty volatile when it's liquid, and the smell was bothering some people in the neighboring lab. And so they pulled the fire alarm on it and cleared out the whole building. And so the hazmat team was in there, like, getting everything cleaned up and turned the heater off. And so it'd go back to solid. And so I basically cleared out a whole building at NASA or at JPL for a whole day and still didn't get yelled at. It's more like, yeah, you guys probably should have thought a little bit about the volatility of that sample. And I'm like, I'm sorry. So anyway, embarrassing story.
All right. So you've got everything together. Everything's worked out, even though you almost probably injured some people in the process. How did you feel then finally as it's heading from JPL to Cape Canaveral? Is that right?
Yeah.
And then you guys got to go down and visit and watch the launch. How did that feel to be able to be there at Cape Canaveral, to have your instrument there ready to launch, to go into space, something that you built heading to Mars to measure the characteristics and attributes of a planet that's millions of miles away?
It was great. I mean, that was super cool. The launch itself was, a little bit nerve-wracking in that, you really hope that all your work doesn't evaporate if something bad happens. But anymore, most of the bad things happen when it's trying to land. So maybe it was not quite that nerve-wracking, but it was, I loved it. I thought it was super cool.
Getting to be there for the launch was one of the most exciting things I've done. I mean, when you're a kid, you dream about just going and being able to see, these spacecraft going into space. And I never dreamed that I would actually see one in person. And I suppose, you can be the general public going down there, but we got on this bus with all the rest of the Phoenix developers and everybody, and we went out underneath this tent, got destroyed by mosquitoes, but there was our little baby flying to Mars, and it lit up the night. And I don't think I ever imagined that I would be there watching that. And it was just really, really fun. It was a great time.
That wasn't even like bucket list stuff. I never really thought about anything like that happening.
Brad, the launch was the party. That was kind of the fun part. I think everything on our mind was all about the landing. We could launch. It was fun to see. It was pretty. But if it didn't land, that was the big thing. And you got to remember that there were a couple other missions that went before us that didn't actually succeed. So whether we could land was still a really big question. They thought they knew why the 2001 lander crashed. They thought it engaged the landing gear and it turned off the jets and it just dropped the last 50 meters or something like that. But they didn't know. And so the question of whether or not we were going to make it safely down was still a big one. So it was waiting for 9 months.
But it did successfully land.
Mm-hmm.
And how long did it take for the TSIP then to be put to use?
Well, they started making atmospheric measurements immediately. So they made the vapor pressure measurements and atmospheric temperature measurements constantly, at least every day. But it was several weeks before they actually inserted the sensor and started making measurements. I think they only had 5 full diurnal periods where they had the TSIP inserted into the regolith to get a full diurnal data set. But the vapor pressure was immediate.
So I guess there's a give and take to be not mission critical. And the give was we could have a lot of freedom with our development and what we put on the board and how that was done. But the other side of it is essentially they didn't want to install or push the sensor into the ground till they made sure they had collected the requisite samples that they wanted to run on the other mech instruments, the wet chemistry.
They really struggled to get a sample into either wet chemistry or the thermal and evolved gas analyzer because the screen, I think, and the electrostatic charge was holding the particles and not letting them in, and they had to get that done to be a mission success. So I think they spent a lot of time on that, if I recall correctly.
And essentially that meant that Doug and we did actually get to go to the command center, which ended up being because the University of Arizona in Tucson led the project essentially. And so they set up a command center, just a business district building. I imagine this, when you go to the command center, it's going to be this just amazing area. Well, it was a building that was left vacant. They actually brought everything for the mission in. They had a special place there that they could run all the commands on the lander that day. So it was in a big warehouse type area, and they had a double of the Phoenix lander that could run all the commands and would essentially do everything that the Phoenix lander was supposed to do that day. They'd run the lander through all these commands and make sure everything worked. And then they'd upload those commands to send them up to Mars, to the actual Phoenix lander. The problem is you imagine, at least I certainly had imagined that this was kind of a remote control thing. We had a joystick here on Earth and they'd be running the remote robot arm and they'd be doing all of these things. And it was just in real time. But no, getting a transmission between here on Earth to Mars, it takes 12 minutes. And so it's not like we're communicating back and forth in real time. They had to put together this whole program, send it over to Mars, and then it would run. And if you did something stupid in that program, then it would do something stupid and you could tank the whole mission.
Mm-hmm. Yeah, and that whole group that was running it was living on Mars time. So the Martian day is not the same as the Earth day. And so they were just steadily moving around the clock on, Martian sols. That was maybe a little bit of a regret, is that I was invited to be on that team, but I couldn't participate because we had just had twins. And so we had 3 kids under the age of 22 months, and I would be divorced right now. So had to prioritize the greater life.
I think you made the right choice, but it was disappointing. When we got down there, we actually were there, I think, start of the 4th month, if I remember well. And so the first 3 months were the ones that were highly funded. It was where everybody was there and everybody was just pressed to the wall. It was this exciting, always on group that was, they were running on the Martian day, but everybody had to be going on around the clock, where they had people analyzing data. They had people preparing the programs. They, after you analyze the data, you had to prepare the experiments for the next day. Did they work? Did they not work? Do we have to do this over? And so everybody was just, this big building had a lot of small rooms, and the teams would go off into these rooms and prepare what was going to happen for the next day. The TSIP had its own room and had its own group of people who'd run off in the room and talk about that. And we got to participate in that one day, but we were not in kind of the flurry of activity.
So everything seemed to have worked out with the instrument then, right? So what were some of the results that you got, and what did we learn from the results of those TSIP measurements?
Well, there were a lot of learnings, I think. I mean, they made those atmospheric measurements pretty much every day, and what they found was that the atmosphere does cool off to saturation, so 100% relative humidity at night, and actually the cold surface, because of radiative heating, scrubs a lot of water vapor out of the atmosphere. So the vapor pressure of the atmosphere actually decreases at night and then increases during the day. And that actually got even more pronounced as the Martian winter came along. The LIDAR detected snow, water snow, and the TSIP, measured the scrubbing of a substantial amount of water vapor out of the atmosphere to the cold surfaces. So that was one interesting observation.
And I mean, critical from this mission really was the actual identification of water on Mars, right? Before there was strong evidence for it, and
Mhm.
they'd even tried to make measurements of it, but the Phoenix lander was able to definitively say that there's water there.
Mhm.
We learned a lot of other things, that water isn't like water you'd want to put into a cup and drink. There's perchlorates and other things in there that make it very salty, and yet we were able to establish that fact.
Yeah. And so, I mean, we talked about the thermal measurements a little bit, the damping depth and the thermal admittance measurements, and those things all came out great. But one of the things that would have been interesting to see, that I would have loved to have seen, was when they actually cleared off the ice, cleared the regolith off the ice. The idea was that maybe solar heating could get that to heat up fast enough to where, instead of sublimating directly away as a gas, you might get some liquid water for just a short amount of time. And unfortunately, that was not measured. We didn't see that with TSIP. So it was a little bit of a disappointment.
Well, one of the things, Doug, that I think really adds to that disappointment is I think we could have done it. And it turns out that there was probably enough power around, if they designed the solar panels just a little bit differently, to be able to light up the lander again after the Martian winter. But as I understand it, the solar panels were not robust enough to be able to survive the CO2 ice that formed during the winter. And
Yep.
and they did try to call it the next year, the next Martian year, and it didn't wake up. But you think of some of these great measurements you're talking about, and that's probably one of my biggest disappointments, is that, maybe with a little more design effort, maybe with a few different things, we could have been in the second year really kind of adding to these measurements, much like Spirit and Opportunity back in the day as they roamed the Martian surface. They were like, wow, look how long we've got. We only planned for 3 months, but I don't remember sitting on a couple of years worth of opportunities or more. And Phoenix, although it was a lander, there was potential to do the same thing, but it didn't materialize.
Mm-hmm. Mm-hmm.
I think for me, I mean, this 20 years of changes, but I certainly wish we had the technology we have for water content now on the instrument then. I mean, it would be probably impossible to do that, but we could measure water content in the regolith. But there's so little water there. Our technology now to detect water, liquid water versus water ice, and even maybe a little spectroscopy that we could do now would be so interesting, and it simply wasn't available to us then. So that's probably, is that a disappointment? I don't know. It couldn't have been, but it's certainly something I wish we could do.
Yeah, I agree.
When we think of the opportunities that we had there for what we had in terms of time and our knowledge at that time, I think the TSIP was fantastic. We were able to accomplish everything that we set out to do and many, many more things. I see opportunities kind of regularly to go on future missions. I think Doug does as well. These are some things we consider fairly carefully. We're still super busy, still unable to imagine these projects. But if we ever went out again to the moon, to Mars, to another planet, there are a lot of these things that I'd love to do again, just to improve some of them.
It's kind of funny that once we built TSIP and it flew to Mars, we, I guess, joined a pretty select club of companies that have flown, hardware. And so people came out of the woodwork asking us to join up with them on these various proposals. And, hey, can you do this? Hey, can you do this? Hey, can you do this? And many of those things we said, no, we're not really interested in. And when I talked about that to some friends in the academic community, some of them are like, are you crazy? That is the only thing I want to do, is to fly something. And you guys are turning down opportunities to be on these proposals. It's kind of funny that way.
Yeah, I mean, it is so fun to participate in these things. It's so fun to be able to do science, off world. But there also is this balance where it's also really, really fun to develop terrestrial instrumentation, and really, really fun to see people be able to be successful in their research here on Earth. So we have to really be careful about how we divide our energies. And so far, we haven't seen the right thing to put us back off world.
All right. Well, that's all the questions that I have. Do you guys want to add any final thoughts?
We at Decagon Meter worked with some pretty incredible individuals as a part of this project. And I don't think I can have an interview like this without just saying a big thank you to Mike Hecht. He became one of our closest friends. I mean, he didn't need to really connect with us like he did. We were a couple of just freshly minted PhD students who didn't know all that much, but he came in and he trusted us. He asked questions of us as if we knew something, and he really made this whole experience an incredible experience. I'd love to do another project with Mike Hecht. And I got to say thank you. He ran that whole mecca. There was the TIGA Doug mentioned, the wet chemistry cell, the optical microscope, and also our TCP. And he did a wonderful job, and it was great working with him.
Okay, our time's up for today. And just a reminder, if you have any questions, feel free to contact us at metergroup.com. You can also reach us via Twitter through our handle @meter_ENV. Our environmental research experts will be in touch with you to answer any questions, or we can put you in contact with today's guest speakers. You can view a full copy of the script in the podcast description. That's it for today. Stay safe, and we'll see you next time on We Measure the World.